Hi guys. So in the last video, we talked about the ideal gas law, PV equals nRT, which lets you solve for something about a gas knowing other things about it. Like, for example, we can solve for pressure if we know the volume, the moles, and the temperature. The combined gas law is a little bit different because it allows us to solve for a change in something when something else changes. So let's just write down the formula. P1 V1 over T1 equals P2 V2 over T2. So if we know the original conditions of the gas and then we make a change, like let's say we change pressure, then we can calculate what the new volume is going to be, or we can calculate what the new temperature is going to be. So instead of just saying like, oh, well, if volume went down, the pressure is going to go up, we can actually say, okay, well, if the volume went down by this much, what exactly is my new pressure is going to be? So important things to keep note of: the temperature has to be in Kelvin. If they give you Celsius and you plug that into this equation, you will not calculate the correct answer. So that has to happen. The volume can be in milliliters or liters. It doesn't matter which one as long as they're both the same unit. So like if V1 is milliliters, V2 also has to be milliliters. But you can use milliliters, unlike in this formula up here where it had to be in liters. For pressure, again, any unit for pressure will be okay to plug in for P as long as they're both the same, meaning P1 and P2. You can't like have kilopascals on one side and ATMs on the other side. Okay? If they tell you that something stays constant, that means you can erase it from the formula. Okay, so the best way to understand this, guys, is to just go ahead and look at an example. Okay, so number one, an ideal gas in a syringe occupies 24.8 milliliters. So that's V1. That's the first volume. 1.12 ATMs. That's the first pressure. By applying the plunger, the pressure is increased to 2.64 ATMs. So they gave me my second pressure. Assuming constant temperature, find the new volume. So I'm solving for V2. So guys, the fact that they told me the temperature stays constant, I can ignore it. Meaning when I rewrite this equation, I can rewrite it without temperature. P1 V1 equals P2 V2. If you did not ignore temperature and you wrote the same temperature on both sides for T1 and for T2, you would calculate the same answer. You would just be working with more numbers. So I would go with what's easier here. All right, so let's plug in my numbers. I have 1.12 for my first pressure. I have 24.8 for my first volume. My second pressure is 2.64. Both are in ATMs, so I didn't have to do any converting. And my second volume is unknown. All right, so let's throw this in our calculator. 1.12 times 24.8 equals divided by 2.64. Okay, so I get 10.5, and I solved for volume. So if my first volume was in milliliters, the volume in my answers has to also be in milliliters. And I know you guys are going to ask about rounding. If I was doing this really correctly, all of my givens have 3 sig figs, so my answer should have 3 sig figs, which it does. I am not going to be grading you based on rounding. So if you don't want to do sig figs, you can round to whatever you'd like. All right. Number 2, this one's going to be a little tricky. A helium balloon is inflated to 5 liters. So there's the first volume at STP. This is their annoying way of giving you temperature 1 and pressure 1. They're saying you temperature 1 is standard temperature and pressure 1 is standard pressure. Now, for temperature, standard temperature is 273 Kelvin. And for this formula, temperature has to be in Kelvin. So that's good. We don't have to convert. Now the pressure, we know a whole bunch of different numbers. I'm going to scroll back for you. We know a whole bunch of different numbers for standard pressure. All right. So we have to think about which one it makes the most sense to pick. All right. So I want to look at what the other pressure is in the question. Pressure 2 was given to me in ATMs. So your 2 pressures have to be in the same unit. So for pressure 1, I'm going to pick 1 ATM for standard pressure so that my pressure units are the same. What will the volume of the balloon be? So we're solving for V2. If the pressure changes to 0.2 ATMs and temperature 1 is 100 degrees Celsius. So I'm not allowed to keep that in Celsius. I have to convert that to Kelvin. So that's going to be 373. All right, so nothing stayed constant here, meaning that I need to plug something in for every variable in my combined gas law equation. All right, so let's do it. P1 is 1, V1 is 5, and T1 is 273. On the other side, I have P2 is 0.2, V2 I don't know, and T2 is 373. Okay, now to solve, guys, I like to cross multiply. You're multiplying 3 numbers together instead of 2. So 273 times 0.2 times x is 54.6x. On the other side, if I cross multiply, 1 times 5 times 373. 1865. If I divide both sides by 54.6, I get 34.2. And I was solving for volume, and the first volume was in liters, so my second volume also has to be in liters. All right, I'm going to give you one of these to try on your own. Okay, Avogadro's hypothesis. So guys, Avogadro's number is that 6.02 times 10 to the 23rd molecules. So what he said, he studied gases. He said if 2 gases have the same volume, temperature, and pressure, they will also have the same number of molecules. Okay, so let's look at these 2 containers here. In cylinder A, I have carbon dioxide, and in cylinder B, I have nitrogen gas, right? And their volumes are the same, their pressures are the same, and their temperatures are the same. So what he says is that the number of molecules, just knowing that the number of molecules in each container would be the same. If you're not happy with that, we can do some math to prove it. So if I use the PV equals nRT formula, right? And I solve for moles. So if I rearrange this and I divide both sides by RT, moles is PV divided by RT. All right, so let's do it. For this container, I have the pressure times the volume over R times the temperature. And in this container, I have pressure times volume over R times temperature. So both containers will calculate to the same number of moles, and we know that in 1 mole, there are always 6.02 times 10 to the 23rd molecules. So you'd come out to have the same answer. Okay, so you have to know the hypothesis. That doesn't necessarily mean they would have the same mass. If you look on the periodic table, carbon dioxide and nitrogen, they have different masses. They're made up of different elements. They could also have a different number of atoms. CO2 has 3 atoms in every molecule. It has 1 carbon and 2 oxygens, and nitrogen has 2 atoms in every molecule. Okay, so the masses and the number of atoms don't necessarily have to be the same, but the number of molecules will be. And that was his hypothesis. Okay, so I'm going to give you guys some practice problems to do. This is kind of using dimensional analysis a little bit, and like for a question like number 79 down here, anything given to you in the diagram, that's your V1, your P1, and your T1. Okay, and then whatever they're asking you to solve for would be on the other side. Whatever's in the question is your V2, P2, T2. Okay, so I'm going to let you guys work on these, and you can do those in the multiple choice. Okay. Extending the ideal gas law, finding molar mass. So guys, this is not a new formula. This is just showing you when we arrange this formula, when we rearrange it to solve for moles, we get PV divided by RT. And I showed you guys that up here when I rearranged it to solve for moles. So we know that moles is PV divided by RT. We also know that the number of moles is mass divided by molar mass, and we know that from the stoichiometry unit. So because both of these things are equal to moles, we can set both of these things equal to each other, and all of a sudden we have a new formula where we can solve for something different. So let's do an example. What is the volume? So we're solving for volume occupied by 36 grams of water vapor. So they're giving us a mass. They're giving us a temperature. And they're giving us a pressure. Okay, so guys, we have to be careful again because when we use this ideal gas law formula, our units have to be very, very specific. So we have mass in grams, that's good. We're solving for molar mass. P has to be in ATMs. So I'm going to say, all right, well, let me write what I'm given. 36 grams. Molar mass is my X. Pressure is 102 kilopascals. And I know in 1 ATM, I have 101.3 kilopascals. So guys, this is going back to that first page again, or that second page of our note packet, where you're using these pressure units as conversion factors. Here I needed to go from kilopascals to ATMs. And I know 101.3 kilopascals is equal to 1 ATM. So I'm just using that to convert. All right, so let's do that in our calculators. 102 divided by 101.3. And I get, the number is 1.006, so I'm just going to round that to 1 ATM. It's close enough. Okay, volume is what I'm finding. Ooh, so guys, I made a mistake. I know the molar mass of water. Water is H2O. And if I look that up on my reference tables, hydrogens, 2 hydrogens weigh 2, oxygen weighs 16. So I know that water is 18 grams per mole. So we're not necessarily solving for molar mass here like was given to us. We're going to have to solve for something else. When they give you the substance, you can just look that up on the reference tables. You're not solving for molar mass. What is the volume? R is my constant, 0.0821, and temperature is 125 degrees Celsius plus 273. Remember that my temperature has to be in Kelvin. So 398. All right. So let's plug it in. My molar mass is 18. My mass is 36. My R is 0.0821. My T is 398. Over. My P is 1. And my volume is X. Okay. So guys, if I just put this over 1 and cross multiply, I get 18X equals 36 times 0.0821 times 398 and if I divide that by 18, I get 65 liters. Okay, so that's if they give you the substance, you're able to use molar mass. Now, because density is mass divided by volume, and this formula has mass divided by volume in it, we can also use this same formula to calculate density. Okay, so let's do this one together. What is the density? I'm solving for that. I'm solving for mass divided by volume. They don't give me a mass or a volume here. So sulfur hexafluoride is that, right? And I can get its molar mass by looking on the periodic table. So 6 fluorines is 6 times 19, plus sulfur is 32. I know this is 146 grams per mole. 300 degrees Celsius is 573 Kelvin. 950 torr. If I scroll back up to my second page, I know that 760 torr is the same as 1 ATM. So 950 divided by 760. 1.25 ATMs is my pressure. All right, so if I have everything that I'm given, let's plug it in. 146 is my molar mass. Density, I don't know. R is 0.0821. Temperature is 573. Over pressure is 1.25. All right. If I cross multiply, I got 0.0821 times 573 So I got 47x equals, cross multiply, 146 times 1.25 equals 82.5. If I divide by 47, I get 3.9. And now I solved for density. So guys, if you think about what my units for mass divided by volume are, my units for mass are grams. And in this equation, volume has a unit of liters. So those would be my units for density. All right, so that's going to be it for today. Here's one more question.